طيب, so today's lecture will be about single cycle processor design. So this is the outline of the presentation. I'm going to show you how to design a CPU step by step. It's going to be a very simple CPU. It's called single cycle because we are going to design a CPU in which each instruction will take exactly one cycle to complete, yani to be fetched and executed in one cycle. This is not the best design. It's a simple design, but in fact, it's a slow design because if you design the CPU like this, you need a long clock cycle to execute each instruction, and therefore the speed of the CPU will be determined according to the slowest instruction that you have in the instruction set. So I'm going to show you first how to design a very simple single cycle CPU. So we'll go into the steps of the data path. What are the components? How do we assemble an adequate data path? How do we control the execution of the instructions? And what is the main control, the PC control, the ALU control? So I will talk about the data path and control in great details. So once I finish this presentation, I will show you how to design a better CPU, a faster CPU. So I will go into the performance and we'll see that what's the drawback of the single cycle and how we can improve it to have a CPU that can execute instructions faster, okay? So how can we design a fast CPU? So we'll use the concept of pipelining and how we can have a pipelined execution of these instructions. Right. So let us start with this presentation. Okay. So the first step is to analyze the instruction set. So before you can do any design, you have to do the analysis. You really have to understand. So analysis really means understanding. Yeah. So you have to understand the instructions. What are the requirements for the data path? So you give a meaning to each instruction. And this meaning is given, this is a hardware meaning. So in terms of the register transfer, so which registers are going to be read, which registers are going to be written by each instruction. So this is what I mean, what I call the meaning. The meaning is the register transfer. Okay, so that's the hardware meaning that we are going to assign to each instruction. We have to include storage elements, okay, as required by the instruction set architecture. So we need registers inside the CPU. We are going to build a data path, okay, that will support each instruction that we have in the instruction set. So the analysis of the instruction set is the first step. The second step is to select the data path components. So here you have to ask yourself, okay, what components do I need, okay, for this data path? So I'm going to show you what are the the components which we need for a simple data path. And also you have to ask yourself how you are going to clock this data path. So the CPU is really a sequential circuit. There is a clock inside the CPU. The clock is very important to synchronize the operation of the CPU. So I will be talking about the clock and the clocking methodology in great details in this presentation. We're going to see how we assemble the data path, meeting the requirements of the instructions. So we put these components together to assemble the data path. And then we have to analyze the implementation of each instruction that we have in the instruction set. So when we do this kind of analysis, we determine the control signals. So we need control signals to control the register transfer, to control the execution of each instruction that we have in the instruction set. So we determine these control signals, and once we understand these control signals, then we can assemble the control logic. So that's basically it. So we have data path, we have control. We'll see that we'll also need some memory elements inside the CPU. So this is how we build the CPU. We are going to have a CPU design project in this course. This project will be announced soon. I'm working closely with the lab instructor, Mr. Saleh, to define your CPU design project for this semester. So it's going to be announced soon. It's going to be on Blackboard soon, so that you can start working on your CPU design project very early, and we finish on time, inshallah. طيب, so let's get started. Okay, let us first start with the first step. We need to analyze, we need to understand what are these instructions. So let us review the MIPS instruction formats. So all the instructions are 32-bit wide. This is great because this will simplify their fetching, their decoding. And notice that the formats are so simple. This is actually one of the best features of the MIPS architecture, is that the simplicity of the instructions and the uniformity of these instructions. You can see that the upper 6 bits of each instruction is the opcode. So these exist in every instruction in the instruction set. Then we have only three formats that we are going to deal with: R type, immediate type, and jump type. So all of them have a 6-bit opcode. In the case of R type, we have 3 registers. So we have to specify what are the register numbers. So we have RS, RT. So these are the 2 source registers, and we have RD, which is the destination. For shift instructions, there is a 5-bit shift amount, which is part of the R-type format. It is just a constant, an immediate constant, which is used specifically by the shift instructions. And there is also a 6-bit function code that appears at the end, which is like an extension to the opcode, which is used only in the R-type format. For the immediate type, there are only 2 registers, RS and RT. RS is always the source, but RT is the destination. It's the target registers. Okay, register in this in the case of the immediate type. And there is a 16-bit immediate, which is a constant, which is part of the instruction. And finally, for the J type, which is used by the jump, we have jump and the jump and link instructions. Okay, so these 2 instructions use the jump type. There is only an address. There are no registers. Okay, it is just a 26-bit address, which is part of the instruction format. So these are the instruction formats. We need to understand them because we are going to deal with these instruction formats when we are going to implement these instructions in the hardware. So when we build these, when we build the CPU, the CPU is going to implement these specific instructions. Right. Let us take a look at the MIPS instructions. Now, MIPS has hundreds of instructions, but we're not going to implement all of them. We are going to implement only a subset of these instructions. So I'm going to restrict my subset to only 16 instructions. So we're going to choose some R-type ALU instructions, like, for example, add, subtract, and, or, XOR, and set less than. The immediate type, we have add immediate, set less than immediate, and immediate, or immediate, XOR immediate. So these actually are very simple instructions. Notice that the shift instructions are not going to be implemented in this version of the CPU. So we're going to keep it very simple. Load and store, only 1 load and 1 store instruction, load word, store word. There are, of course, other load and store instructions, which are defined by MIPS, but we are not going to implement them, just to fit everything within a single presentation. Otherwise, it will take a long time to cover all the instructions. So the point here is really, we do not really want to implement every instruction that exists in the MIPS instruction set. We would like to keep these instructions to a minimal number of instructions, which are sufficient to illustrate the design of data path and control. So really, these instructions will illustrate, okay, how we can design data path and control without going into the details of every instruction that exists in the instruction set. We are going to implement only 2 branch instructions, branch if equal, branch not equal, and 1 jump. Notice that the jump and link is not going to be implemented, but I will leave it for you to think about it, how we can implement the jump and link also inside the CPU. So jump and link is essential to support functions. Also, jump register is not going to be implemented to return from a function call. So there are many other interesting instructions that we can, of course, add to this minimal subset. So this minimal subset is going to illustrate really the concept and the which are behind the design of data path and control. We can, of course, add more instructions if you want to, but the concepts are still the same. So we just follow the same concepts, okay, to implement this subset, to implement any set of instructions. Okay, is this clear? That's what I'm going to do in this presentation. Right, so feel free to interrupt me if you have any question. So this is the list of 16 instructions that we have seen in the previous slide. Notice that the first 6, less than here, first 6 are of the R-type format. Notice the opcode equal to 0. We have 3 registers, RS, RT, RD, and each instruction has a unique function code. Okay, so these are R-type instructions. Notice that I did not include here the shift instructions. There is set less than, but there is no set less than unsigned. You can, of course, add this if you would like. So this is the signed set less than, okay? For the ALU immediate, I have add immediate, set less than immediate, and or XOR immediate. So these are 5 ALU immediate instructions. Notice that their format, okay, each one has a unique opcode. There is only RS, RT, there is no RD. It does not appear in this format. So there is a 16-bit immediate, okay, which is part of the I-type format. So my immediate here is my second operand, and RT is my destination. There is load word and store word. They are also of the immediate format, but these 2 instructions are going to access memory. And the immediate is used for displacement. RS will contain the base address. RT can be the destination in the case of load word, or it could be a source register in the case of store word, because we're going to store the value of RT in memory. Notice that the branch if equal, branch not equal are also of the immediate format. However, the 16-bit immediate here is a PC relative offset, which is used to calculate the address of the target of the branch instruction. So we are going to compare 2 registers, RS and RT. So both RS and RT are source registers in the case of the branch instructions, and the immediate, the 16-bit immediate, is used as a PC relative offset. It is just a constant, which is part of the instruction, but we add it to the program counter to calculate the target address, okay, the branch target address, where we would like to branch, if the branch is taken. And finally, we have the jump. Notice that the jump here has a unique opcode, and it has a 26-bit immediate. So these are the details of the MIPS subset. Now, these details are very important because we are going to implement these instructions. So you have to go into these details. Without these details, you will not be able to implement these instructions. So we're going now to go into the implementation. So this is the analysis part, okay? Now what we have to do is that step number 2 is that we have to give a meaning to these instructions. And the way that we give a that we describe the register transfer level. So before we build the logic, we need to give a meaning, a hardware meaning to these instructions. So for example, what's the add instruction? So when you have an add instruction, here like add, okay, what the CPU is going to do is going to read the values of two registers RS and RT, and is going to add them. So the ALU is going to add them, and then the result is written into register RD. So RD here, so the result of this computation will be stored in destination register RD. So this is the register transfer. This is the register transfer. So we are reading two registers, RS and RT. The ALU is doing the computation, and the result is written into register RD. At the same time, PC becomes PC plus 4 because we have to point to the next instruction. So once we have completed this, the execution of this instruction, the program counter should be incremented by 4 to point to the next instruction in memory. The same thing can be said for subtract, except that the ALU is going to do subtraction, not addition. So we have to control the ALU to do subtraction. In the case of OR immediate, okay, what we have to do is that my second operand here is a 16-bit immediate, which is part of the I-type format, and the result is written into register RT. So RT here is my destination register. Notice that we always increment the PC by 4 after completing the execution of this instruction. Load word, we need to access memory. Store word, we need to access memory. So in the case of load and store, we calculate the memory address. So the effective address in memory, it will be the value of register RS plus the 16-bit immediate. Notice that the 16-bit immediate is sign extended to 32 bits because the immediate can be negative. So for this reason, we have to do sign extension, not zero extension. Whereas in the case of the OR immediate, we do zero extension because the immediate is unsigned. Whereas in the case of load and store, the immediate is signed. So we do here address calculation. And then once we have calculated the effective memory address, what we have to do is that we have to access the memory, and we have to transfer the data from memory into destination register RT. So notice that RT is my destination register in the case of load word. In the case of store word, RT is a source register. So what we have to do is that we have to read the value of register RT, and its value will be written in memory. In the case of a branch, what we have to do is that we have to read two registers, RS and RT. We have to compare them for equality. And if they turn out to be equal, what we have to do is that we have to calculate the branch target address. So here we use the 16-bit offset, which is part of the instruction format. Remember that the branch is of the immediate type. So this 16-bit offset, it is just a constant, which is sign extended because it can be negative. We multiply it by 4 because each instruction is 4 bytes, and we add it to PC plus 4. So it is PC relative addressing, but not relative to the branch. It's relative to the instruction that appears after the branch. Remember that PC plus 4 is the address of the next instruction appearing after the branch. So therefore, we branch relative to the address of the next instruction in memory. This is how it's defined in the MIPS architecture. Now, that's if the branch is taken. Else, it means if the branch is not taken, then simply PC is equal to PC plus 4. So all what the branch does, so the meaning of the branch instruction is that it only modifies the program counter. That's all what it does. It does not rewrite any register inside the register. So it does not modify any of the general purpose registers. It only modifies the program counter. That's what it does. It's a control instruction that modifies the program counter. Any question about this? So this is what I mean here by the register transfer level. Okay. Okay. So I can go slightly into more details by splitting I can go into the fetch execute cycle. So basically, I can say that each instruction will take a certain number of steps. So first, we have to fetch the instruction. So in order to implement these instructions in the hardware, what we have to do is that we have to fetch the instruction. So the first step is to fetch the instruction. So we use the program counter to fetch the instruction from memory. So the PC contains the address of the instruction. So first we have to use this address to fetch the instruction. So once we have the instruction, we can examine the opcode, we can examine the function code. If we have an R-type instruction, according to the opcode, we know that because opcode 0 is used for R-type. So we know from the opcode it's an R-type instruction. So once we have, so this is called instruction decoding. We examine the opcode. This is part of the control of the CPU. Right. So if we know that this instruction is an R-type, what we need to do is that we need to read two registers. Okay. So we need to read two general purpose registers, RS and RT. So we get data 1 and we get data 2. So data 1 is the value of register RS, and data 2 will be the value of register RT. So the instruction can specify any two source registers. So the register number is stored inside the instruction, but data 1 and data 2, these are 32-bit values. Okay, so these are the values that we are going to read, okay, from the register file. So the register file contains all the general purpose registers, and we need to read two. So after we read two, we have data 1 and we have data 2. What we have to do is that we have to execute the instruction. So now when we would like to execute it, we are going to use a component inside the CPU. This component is called the ALU. So the ALU is the arithmetic and logic unit. Okay, it is a component inside the CPU, which is used for executing, okay, the instruction. So we pass data 1 and data 2 to the ALU, and also we pass the function, because the function will specify the operation. So for example, add will have a function, subtract will have another function, and or XOR, these have different functions. So therefore we pass the function, we pass data 1, we pass data 2. The ALU is going to compute a result. So this is my ALU result. Once we have the ALU result, this ALU result should be written in the destination register. Okay, so after executing, we write the ALU result into destination register RD, and then we increment the program counter by 4. Notice that this step is independent of the previous steps, because this is an R-type instruction, so we simply, just an ALU instruction, we just need to just increment the program counter by 4, and we are done. Okay, so once we have finished all of these steps, we are done. Some of these, so the last step can be done in parallel with the above steps. The above steps have to be done sequentially. And we have to fetch first, then after fetching, we examine the opcode. If it is an R-type ALU instruction, then the second step will be to fetch the operands. And then after reading data 1 and data 2 from the register file, then the third step would be to execute. The fourth step would be, okay, to write the result into the register file, to write the result, ALU result, in the destination register RT. And there is a fifth step here, which is PC equal to PC plus 4, but we don't really have to execute this fifth step sequentially because it does not depend on the previous 4 steps. Well, it depends, of course, on the first step, because we have to know that, okay, we have to fetch before we can actually increment the PC. Right, so how about an immediate type? In the case of the immediate type, again, we fetch the instruction. That's the first step. Then we read data 1, but data 2, we don't need it from register RT. Data 2 is the immediate. Okay, so what we have to do is that we have to extend the 16-bit immediate. Now notice that data 1 is 32 bits because we are going to read it from register RS. So each register contains 32-bit. So the data 2 is going to be extended. So the immediate is only 16 bits, but we are going to extend it from 16 bits to 32 bits. Okay, so that's my immediate constant. Now we are going to execute. We're going to use the ALU to execute, but we use the opcode. So the opcode is going to specify the ALU operation. If you have add immediate or immediate or end immediate, we use the opcode to specify the operation for the ALU. The ALU is going to compute the result. this result is written into register RT. So notice that in the case of R type, the destination is RD. In the case of the immediate type, the destination is RT. It's a different field in the instruction. There is no RD in the case of the immediate type. So the I-type format does not really have register RT. It has only register RT. So RT becomes my target register for the immediate type. And then we simply increment PC becomes PC plus 4. That's in the case of an I-type ALU instruction. We know this based on the opcode. After we fetch the instruction, we can decode the instruction, we can examine the opcode, and the opcode will tell, okay, the control logic inside the CPU that this is an I-type instruction. We can do the same thing for the other instructions. Yani, for example, in the case of a branch. Now, in the case of branching, we are not going to write a general purpose register RT. No, we are going to modify only the program counter because a branch is a control instruction. So the fetch execute sequence is different. Okay, in the case of, so the fetch execute cycle actually is different. So the first step is to fetch. We always fetch. That's always is the first step. Okay, because you have to fetch the instruction before you can examine it. So when you decode the instruction, you examine the opcode. Now the opcode can tell you that this is a branch instruction, and it's branch if equal or a branch not equal. We have many branch instructions that exist in the MIPS instruction set. So the opcode will tell you exactly which branch instruction that you are decoding now, after you have fetched the instruction. So we know this from the opcode. You can read two registers, RS and RT. So this is data 1 and data 2. So notice that data 2 is the value of register RT. So RT now is my second source. So even though it's of the immediate type, but it's not an ALU instruction, it's a branch instruction. So therefore, we have to read the value of register RT. Now we have to compare. Why? Because I would like to see if so I have to compare before I branch. So I have to detect, okay, I have to check the CPU, of course, not me. The CPU, sorry, the CPU is going to check, okay, whether data 1 and data 2 are equal, okay? So therefore, we can use the ALU to do subtraction. So to check for equality, you can subtract data 1 minus data 2. If the result is 0, that's an indication of equality. So you can use the ALU to do subtraction because the ALU does subtraction. It supports subtraction. So use the subtract operation and then check if the result is 0 or not 0. So what we need is just a flag, okay, a flag that indicates equality. So if this flag, okay, if they are equal, the 0 flag will be equal to 1. If they are not equal, the 0 flag will be equal to 0. So if they are equal, if the 0 flag equal to 1, then what we need to do is that we need to branch. So when we need to branch, we modify the PC differently. So we modify the PC, we calculate it like this. It's PC plus 4 multiplied by the sign extended offset. So the offset is part of the instruction. It's just a 16-bit constant inside the instruction. So we have to sign extended because it can be negative. And then we have to multiply it by 4 because all the instructions are 4-bit long. Sorry, they are 4-byte long, not 4-bit, 4-byte long. 32 bits means 4 bytes in memory, and memory is byte addressable. So therefore, we multiply the constant, the offset by 4, okay? And then we add it to PC plus 4. So this will calculate the branch target address, where I would like to branch. So by calculating the PC like this, the branch will be taken. Else, it means that they are not equal. Then simply, this is the else, then simply we have to say that PC equal to PC plus 4. So this is all what the branch does. Okay, so it compares and it branches if the branch is taken. It does not branch, it goes to the next instruction if the branch is not taken. Okay, so these are examples, R-type, immediate type, branch if equal. I have more examples like load and store and the jump. Now these are different. You see that here the fetch execute sequence is different. So again, we start by fetching the instruction. I need to read the base address. So the base register, so this is the value of RS. RS is the base. We calculate the address as base plus the sign extended immediate. So this is displacement addressing. So we add the value of register RS plus the immediate constant. So once we have the address, once we have calculated the address, we need an extra step to access the memory. So we access the memory at this specific address. So we have to read the data from memory because this is load. So the data has to come from memory. And the value of register RS is nothing but an address. It's the base address. So once we have calculated the address, then we access the memory at this specific address and we load the data. So we have to read this data from memory. So once we have the data, then we can write register RT with this data. Okay, so we have loaded the data from memory. We have transferred the data from memory into register RT. So now we have the data in register RT. So RT is my destination register. And then we just increment the PC plus PC becomes PC plus 4 so that we point to the next instruction in memory. Yes, Ali.
Doctor, when we access
Yes.
the memory address, it will return the data as it represented. Like for example, in the memory, I'm saving value -2, for example. It will be
Yes.
returned the data -2, or should the CPU try to translate this data and represent it
Well, no.
-2?
Well, okay. Yeah. So the load. So when you transfer the data from memory into into the CPU, in the case of load word, we specify the memory address, but we don't load 1 byte. We load 4 bytes. So 4 bytes will be transferred from memory into a register. Okay. So there is no modification to these bytes. We just take them from memory and we place them inside a register. Okay, so 4 bytes are transferred because this is a load word instruction. If it was a load byte, we only transfer a single byte and then we extend it, okay, from 1 byte to 4 bytes so we can fill the upper bits inside the register. But here, okay, there is the load word is going to transfer 4 bytes, okay, from memory. Now notice that we have 4 bytes starting at the memory address that we have calculated. So if we are using the little endian byte ordering, so the first byte will be in byte 0, then byte 1, then byte 2, byte 3. So we fill the bytes inside the register, starting from the least significant byte until we reach the most significant. So this is the importance of the byte ordering, because this is how we fill the bytes inside the register when we transfer 4 bytes from memory into. So when we load, okay. So already we have the data is in binary. For example, if you are going to, let us say, if the data is -2, it will be stored -2 using 4 bytes in memory. So 4 bytes are allocated for your data in memory. Of course, you should have allocated the data, and then you start loading it. Okay, for example, if you have an array, each element will be 4 bytes, an array of integers. Then each element will be 4 bytes. You use load word to transfer one element of the array, 4 bytes. Okay, of course, the value will be in binary inside memory, and when you are transferring it, you are transferring them as bytes. That's it. Is this clear?
Yes, clear.
Okay. Now, in the case of store word, what we are doing is that we are transferring the data in the different direction. So again, we fetch the instruction. This will be the first step. Now, here, what we have to do is that we have to read 2 registers. RS will be the base address. So notice that here, when we fetch the registers, we fetch register RS. So this will give me the base address. But we also read register RT. So RT now will contain my data. So what I really need, so the store is going to write the data in memory. So we are writing memory. In the case of load, we are reading the data from memory. So we calculate the address exactly the same way like we have done in the case of load. So we add the base address, which is the value of register RS. Remember that this address is 32 bits because the value of register RS is 32 bits. We add it to the 16-bit immediate, but of course we cannot add 32 plus 16 bits. So what we have to do is that we have to sign extend the 16-bit immediate into 32 bits, and the ALU is going to do address calculation. Okay, so what you get is just you get the address, and then what you have to do is that you have to transfer the data. So the data is the value of register RT. So you transfer 4 bytes from the CPU into memory. Okay, so we are writing memory at this specific address. So you specify the address of the memory and you specify the data that you would like to write in memory, and the data will be stored in memory. 4 bytes will be written in memory. So these 4 bytes can represent an integer, a 32-bit integer. And again, we use the little endian byte ordering. Okay, so the byte ordering is very important because we are storing 4 bytes starting at this specific address. So byte 0, then byte 1, then byte 2, then byte 3. This is how they will appear in memory according to the little endian byte ordering. Some CPUs use the big endian byte ordering. For example, IBM has some CPUs, its own CPU different from MIPS, that uses the big endian byte ordering. So the bytes will be written in the reverse order. So we start at byte 3, then byte 2, then byte 1, then byte 0. So basically the bytes will be reversed in memory. And then after that, we just simply increment the program counter after we are done, okay, so that we can point to the next instruction in memory. And finally, I have the jump here. Now notice that in the case of the jump, all what I have to do is just to jump. Okay, so there is no need to read any register. So we fetch the instruction. Notice that the fetch is always done step because you cannot do anything without having the instruction. So you fetch the instruction using the program counter. So the program counter contains the address. Once we have fetched the instruction, what we need to do is that we need to calculate the target address. According to the MIPS architecture, okay, the addressing mode for a jump is not PC relative. It's like direct addressing. So you take the 26-bit address directly from the jump instruction, you concatenate it with 00. So the 00 always will be the least significant 2 bits because remember that all the instructions are multiple of their addressees. All instructions are 4 bytes, so their addressees are multiple of 4 and aligned in memory. So the least significant 2 bits of the address is so these least significant 2 bits are always 0 and 0, okay? Because the address is multiple of 4. So when you look at a number in binary and it ends with 00, you know that this number is multiple of 4, okay? And then you take the upper 4 bits of the program counter. So these upper 4 bits are unchanged, okay, in the target address. And you change the PC according to this target address. That's it. So there is no need to read any register. There is no need to write any general purpose register. The only register which is modified is PC, because by modifying the PC, you will jump, okay? So the jumping will happen when you modify the PC. You don't go to the next instruction. You can jump anywhere, okay, in memory, according to the target address. So this is the jump target address. Yes, Khalid, you raise your hand.
Yes, Doctor. In the slide that you were explaining the registers types, there was no 00 in the register. It was only the first 26 bits for the address and the remaining 6 parts for the operands.
Yeah, but these 0, okay, yes. This 00 does not appear inside the instruction. This is inserted by the hardware inside the PC register, okay? So the address is only 26 bits inside the instruction, but the 00 are forced by the hardware. So this is part of the implementation of the CPU, is that the CPU is going to insert the 00 inside the PC register itself, the program counter register, so that the PC address, because the PC contains the address, of the instruction will always be multiple of 4. Okay. Right. So this is basically the instruction fetch execute. So now we gave him meaning. You see, this is register transfer. We gave him meaning. We break down, okay, the fetch execute cycle into multiple steps, starting from fetching the instruction, decoding the instruction. Now, of course, we know it's a jump based on the opcode. So after we have fetched the instruction, I did not really show it here, but the opcode will tell us that this is a jump, this is a load, this is a store, this is a branch. We know that from the opcode, okay? And then after that, the CPU, of course, we have to control the execution of the instruction so that the instruction will do what it is supposed to do inside the CPU. Right. So we have seen that the meaning. Now, from this meaning, we can put some requirements, okay, of the instruction set. Now, we need an instruction memory. We need memory, okay? So we need a memory where we would like to store all the instructions. Okay, so we have an instruction memory, and I need another memory, a separate memory, which is called the data memory, where I would like to store my data. So there are two memories inside the CPU. One is called the instruction memory, and the other one is called the data memory. Today, of course, these are different from the main memory. So today in modern CPUs, these are called caches, cache memory. It's like a small memory inside the CPU. I'll come back to this topic later toward the end of the semester and talk about cache memory in great details and how it's organized. This is actually a topic on its own, so I will keep it until later. So now think about the instruction memory and data memory as like a small memory inside the CPU, and think that the entire program, assuming that usually the cache memory is small, but we're going to assume that the entire program can fit inside this small instruction memory, and all the data can fit inside this small data memory, which is really data. Now we need registers, because this is the requirement of the instruction set. The instruction set says that we have 32 registers. In fact, we have only 31 because R0 is hardwired to 0. So we only need 31 registers, general purpose, and each register will be 32 bits. Okay, so this is also part of the requirement. We need registers. Okay, so we can put all of these general purpose registers in one register file. It becomes like a component inside my CPU. I need a program counter. So I need this PC register. Okay, so this PC register is essential, because without the PC register, I cannot control the execution of the program. So the PC register is an essential register, because it will store the address of the instruction that should be fetched and executed. And at the end of the execution of each instruction, when we finish an instruction, we update the PC. So the PC will be updated to point to the next instruction. Unless we are branching or jumping, then it will be updated according to the target of the branch or the target of the jump. So we need also an adder. Okay, we need an adder to increment the PC, because every time I finish the execution of an instruction, I need to increment the PC. So you see that now we start analyzing and understanding what are the requirements. Okay, so based on the meaning that we gave to these instructions, we can see that, oh, I need this component, I need this component, okay, and so on. I need, an extender is actually something which is very simple, okay, for immediate constants, because when you add 32 bits plus 16 bits, you have to extend the 16 bits. Okay, the immediate is only 16 bits, so it has to be extended to 32 bits before we can, for example, when you have an ALU immediate. So if you would like to use it inside the ALU, it has to be 32 bits. We need an ALU. Okay, of course, we cannot execute any instruction if there is no ALU. So this is an essential component inside my CPU. Right. So let us talk now about data path components and clocking. This is now my second topic. Now, these are the components of the data path. Some of these components are combinational circuits, so I call them combinational elements. And some of them are storage elements. Okay, for example, an instruction memory, a data memory, a PC register, and the set of registers or the register file. Okay, so these are called storage elements. So the combinational elements will be like the ALU. The ALU is pure combinational. It has no memory in it. You provide the inputs, you get the outputs. So this is the ALU. So the ALU has two inputs here. Okay, you can actually have here your first data input. So this is shown here. Notice that these are 32-bit inputs. Okay, so this is my data. It also has the ALU operation, which is used to control. Notice that my control input, I'm showing it in red. So we need to control the ALU. We have to specify what is the ALU operation. So we have to tell the ALU whether to do addition or subtraction or any logic operation or shift operation. The ALU is going to produce an ALU result. This is the output. It's a 32-bit ALU result. Now, sometimes if you would like to detect overflow, for example, when you are doing addition or subtraction, you can have an overflow output. So ALU can generate a flag as an output here, which is overflow. If you would like to compare, like in the case of branching, you would like to compare for equality, you can have a zero flag. The zero flag here indicates when you would like to compare the two inputs, you can use the ALU for comparison. Okay, it can produce a zero flag. A multiplexer is shown here. This is my multiplexer. It has two inputs, it has an output. There is also a select input. The select input can select whether the output should be input 0 or input 1. The multiplexer is very, very useful component. You have studied multiplexers in the 202 course. We're going to use multiplexers all over inside when we build this data path of a CPU, we're going to use multiplexers a lot. And extenders can extend, this is also a combination element, it's going to extend a 16-bit constant. You can see here 16-bit, and the output will be 32 bits. We can control this extender. We can actually use it for zero extension, or we can use it for sign extension according to the sign bit of the 16-bit immediate. The storage elements are shown here. Instruction memory, we have data memory, we have PC register, which is shown here. We have the register file. Notice the clock, how it's connected to the PC register. Notice the clock, how it's connected to the register file, how it's connected to the data memory. I'm not connecting here the clock to the instruction memory because we only read from the instruction memory. But in the case of the PC register or the register file or the data memory, we're going to write. So the clock is essential for timing the right operation. Okay, so that's the importance of the clock. It indicates when we should update a register or when do we update memory. Okay, so the data memory can be read, it can be written because we have store instructions are going to write to the data memory, so we need the clock. Also, the PC register is going to be written. Every time we finish the execution of one instruction, we have to update the PC register, so therefore we need to time. Okay, we have to indicate when to update the PC register. We have to indicate when, okay, the register file should be updated. So these are actually my components. These are my building blocks, okay? So I need to talk about my building blocks because I'm going to build the CPU using these blocks. So next lecture, I'm going to pause now here. Okay, so this is the end of my lecture today. Next lecture, I will go into the details of these components. And we see how we can actually build these components. We go into their details. And then after that, we see how we are going to build a CPU with the data path using these components. And then we will look into the control. How do we control the execution of these instructions?